Last time we derived the equation of motion of a field, which is also called the Euler-Lagrange equation, starting from the principle of least action or variational principle. And we showed that, and the way we derived now this derivation, it is just like deriving Euler-Lagrange equation in classical mechanics from action principle. Only difference is that here the entities which play the role of coordinates at the field phi, and they are functions of x and t. In classical mechanics, these coordinates are q, q dot, etc., and they are functions of t only. But here, since the coordinate is chosen as phi, they are functions of two parameters, x and t, and x and t. Because of that, in that derivation, not only variation derivatives with respect to time, space derivatives also you have to consider. Because of that, your Euler-Lagrange equation takes this form, okay, where in classical mechanics earlier this was only del del t, this was only del del t, but now since there are x and x now enters in the description of the field phi, which is the coordinate here. There's another parameter, you can look at it that way. Therefore, x also comes in the variational principle in the Euler-Lagrange equation. Is this derivation of this equation clear? Is there any question about derivation of this equation, Euler-Lagrange equation, from variational principle? If it is clear, then you can also see, if you can remember the classes of classical mechanics, there are certain symmetries of the Lagrangian that if you multiply by a Lagrangian by a constant, the equation of motion will not change. Okay. Similarly, if you in a classical mechanical Lagrangian, if you add a total derivative of a function of coordinate and time, the equation of motion will not change. Do you remember this, or can you prove this? Two Lagrangians which differ by only a total derivative of time in classical mechanics, these two Lagrangians will give you same equations of motion.
At boundary, it's
Yeah,
to zero. Total derivative comes to zero.
yeah, because of that reason. Similarly, here, if you have two Lagrangians, if this Lagrangian satisfies this equation, and there is another Lagrangian which is now their space is dependence is also there. Therefore, not only time derivative but a total derivative of like this, a quantity like this, delta mu, say k mu, k is another quantity. It is a total derivative. Clear? But here, since space is an extra parameter, so this term is there. Because of this term, if we put this Lagrangian in place of this L, if L satisfies this total thing will also satisfies this. That means they are same equations. Okay, that means two Lagrangians separated by this kind of things by a total derivative should correspond to same Euler-Lagrange equation or same equations of motion. So Lagrangians are arbitrary up to addition or subtraction of any total derivative term. Okay. So if I want to find a Lagrangian for any equation of motion, which we will soon find, we can easily add or drop to make our calculations handy. We can easily drop or introduce any total derivative term in the Lagrangian. Okay, because that is, we can add it arbitrarily, this term, the end of terms, which will not change equations of motion. So Lagrangians are arbitrary up to addition of a total derivative term. We will make use of this in future. Now, once we, this is the equation of motion of this field is xi, okay, and you remember that xi, this whatever it's called xi, that xi r is the is some discrete index where r represents the number of fields, number of different kinds of fields which is used to describe the system. So you are describing a system, and your system is such that it can be described by a number of fields. For example, R can be, for an electromagnetic field, R is, there are 4 values of R, one for the scalar field phi, and other 3 for these fields, A1, A2, A3. Vector potential, 3 components. So these 3 enters here, this 4 enters here, okay. So the R is 1 to 4 for electromagnetic field. So your electromagnetic field is described by all these 4 fields simultaneously. You need all these 4 fields. Now, it may be that some may not be, I mean, okay, leave it. So once I know the Euler-Lagrange equation, which is the equation of motion of the field, you can check or given an equation of motion of a field, how can I find the Lagrangian of this field? Suppose we are discussing in the context of fundamental particles. We want to know their interaction theory. For that, we first introduced how we can describe the free fields, free particles, and free particles being relativistic and microscopic. Their description should be either like this or this, okay. And this has some problem we have seen regarding probability density, which is negative, which is not there here. But anyway, there are 2 relativistic equations for this field. Now, this is equivalent to the Euler-Lagrange equation. So what I want to know is that what should be the L for this Klein-Gordon field, so that if I put that L here and do the derivatives and work out, we will get Klein-Gordon equation. So for what L, this equation where xi r should be replaced by phi, this L will give Klein-Gordon equation, and for what L, this equation will give Dirac equation. Okay, so basically we are asking this question: what are the Lagrangians corresponding to these above equations of motion, which are Klein-Gordon or Dirac? So we will survey that now.
Sir.
Yes.
Hello.
Yes.
So when we have the equation of motion, and then why we need the Lagrangian?
Because Lagrangian is a single function, okay, single function which captures all the symmetries of the system. Those things are already there in the equation of motion, but it is a differential equation of equations of motion. If we want to further probe the system, either we have to solve this system, or we have to look at the properties of this differential equation. But looking the properties of this partial differential equation or its solution, it is always elegant, or it is always useful or less clumsy to look at the Lagrangian itself, which is a single function. Okay, so all these dynamics of these fields are captured in this Lagrangian, because this Lagrangian and these equations are just connected by some mathematical steps. They are equivalent, exactly equivalent. So whatever the information content of the equations of motion are already contained in the Lagrangians. Like when you did classical mechanics, suppose you are solving this central force problem, you can either look at the equations of motion and solve it and gain some information about the system. But you can also look at directly the Lagrangian and look at the symmetries of the system directly from there. You don't need to go through solving that equations of motion. Okay, you can directly, so far as the symmetries of the systems are concerned, and symmetries tells you almost everything about the system. So the function, you have to look at the symmetry. So Lagrangian is that function where which you can test which symmetries it does have for different transformations. From that investigation, you can extract details about the system without solving the differential equation of motion of the system. For this reason, this is the same reason why we do Lagrangian formulation for any theory, for any classical mechanics or even this, because Lagrangian presents you the single function. So now you can it is easy to deal with a function rather than a differential equation and partial differential equation, I mean, to be correct, and its solutions. Clear?
Yeah, got your point.
Now, so this is the motivation for finding out express the dynamics of Dirac field, Klein-Gordon field in terms of the Lagrangians. And this will be required for the rest of my course and quantum field theory course. Sanjay will not may teach this, I don't know, but he told me to teach this Dirac Lagrangian and Klein-Gordon Lagrangian and the different transformations on this Lagrangian, like Lagrange transformation, parity, charge conjugation, etc. I will do this in this course. For this purpose, I am introducing this concept. Or I am doing this, finding this Lagrangian for this field. So basically, we have to find this Lagrangian for this field, so that when put in Euler-Lagrange equation, it gives us the Klein-Gordon equation. Let's start with the Klein-Gordon equation. Okay. Now remember, okay, so this is Klein-Gordon equation. And you know, Klein-Gordon field is a scalar field. It is under Lorentz transformation. Under Lorentz transformation, it does not change. Clear? So this is the Lorentz transformation property of the field. We have to find its Lagrangian. So we have, now there are two possibilities. One possibility is that this equation may be satisfied by a real number, real field. So one possibility is this phi is a real complex function, a real function. That means phi is equal to phi star. Now, if phi is equal to phi, if it is a real number, if phi is a real number, then you need only one number to specify this. Okay. So this equation involves only one quantity, which is phi, which is this. So equations of motion is this, which is the Klein-Gordon equation. This one phi, one single real phi satisfies this equation. If it is a complex Klein-Gordon field, complex scalar field, that means phi not equal to this. That means if you want to extract really how many real number degrees of freedom this phi have field wise. So this phi is, you can write it in terms of, it has two terms. One is the real part, another is the complex part. Okay. Now basically, a description of a complex scalar field needs basically knowledge of two real fields. Clear? Therefore, when the phi here is complex, and the phi here in the Klein-Gordon equation is complex, you basically need two real scalar fields to describe this whole system. Therefore, you can think the same Klein-Gordon equation in terms of two component real fields as this. Clear?
Hello.
Yes.
So why are we calling it a scalar field? I mean,
scalar field means any field which does not transform under Lorentz transformation is called a scalar field. You can check So this is the equation of motion of this field. This equation must be of Lorentz covariant, must be in the form of, must exhibit Lorentz covariance when you perform Lorentz transformation. That means the form of the equation should remain invariant because it is an equation of motion, relativistic equation of motion for a field phi. Its form will remain invariant under Lorentz transformation. Now you can check that this quantity, this operator, does not change under Lorentz transformation. Because of this whole delta, this part is invariant under Lorentz transformation. This form of this function. So if you do Lorentz transformation, del mu is always equal to del mu prime. You can check this. Use the Lorentz transformation equations to check this. If this is so, then this quantity should be a Lorentz invariant, or the form of this quantity should not change under Lorentz transformation. That for unchanged, I mean, invariance of form is called by the word covariance.
Covariance.
Therefore, since this form will not change, and this equation as a whole should remain invariant under Lorentz transformation because it is the equation of motion. Therefore, phi should also not change.
Sir, is the mass the rest mass of the particle?
Yes, that is the rest mass of the particle. Because this equation is obtained by replacing E square equal to E square plus M square by replacing E by I del T and P by minus IH cut del X. Okay, but or del.
And using the commutation relation between E and del X.
Huh?
I mean, you have to use the commutation relation between E and nabla.
E and you don't need, in deriving this equation, we don't need any commutation relation. You just replace E is this operator. You use this prescription IH del tau. P is, you can check the class note, previous class notes, it is there. IH nabla for this. You put these terms here in this equation. So you get square of this is equal to square of this plus M square. So sorry. This is not square. So once you put it, it will get squared, plus M square, and these are operators. So you have to introduce a field, a function on which it will operate. That function is psi. So that's how you get this Klein-Gordon equation. M is the rest mass of this particle because M sits here. Now,
I have another question.
yes.
What's the problem with a real scalar field? I mean, why are we invoking the complex scalar field in Klein-Gordon equation?
There is no. I have not said any problem with real scalar field. I am saying that this is a differential equation. This phi can be real, can be complex. I am studying these two cases separately. I am not giving any one priority over the other. Both has their significance. Okay, I am not telling that real scalar field has a problem. No, it has no problem. It is a field. It can be scalar, it can be complex, but I want to show you that when it is real, how to deal with this, and when it is complex, how to deal with this. There is a slight difference between the dealings of these two cases. That's why I am, so I said case 1 and case 2. Yeah, I'm not saying it is a problem.
Okay.
So when it is complex, so you have basically this boils down to existence of two real fields like this. Okay, so these are phi 1 and phi 2. This phi 1 and phi 2 satisfies these two equations. So if you really want to think in terms of real field, then you can think complex field, a complex scalar field is basically dynamics of two real fields. You can look at that way. Okay, so your system of fields is now two real fields, phi 1 and phi 2. If you want to write the equations of motion, then you have to write two separate equations of motion for that. One is this, because that corresponds to this R. R is equal to 1 and 2. If you put phi 1 and phi 2 here, you can break up in terms of real fields. Real fields means a complex thing has a 2 real degrees of freedom. In that sense, we are separating out the real degrees of freedom. And in terms of those real degrees of freedom, we are seeing that. Because we will see that this kind of things has very, when ultimately when we relate it to fundamental particles, we will see this. Okay. So how the real scalar field is connected to fundamental particles, how a complex scalar field to fundamental particles. Just to give you an idea, let's say if a like pion, there are 3 fields, pi 0, 3 particles, pi 0, pi plus, pi minus, you know. This pi 0, all this is spin 0. So they are replaced, they are described by scalar fields. Pi 0 is represented by a real scalar field. Pi plus and pi minus are represented by complex scalar fields. Okay, and complex scalar field has 2 degrees of freedom, 2 real parts, which one corresponds to this, one corresponds to this. You can think like that way. Okay, but let's not ask any questions here. I will come to this later. Just to make you assure you that this both are important. Okay, both real field and complex field has their own significance. Now, the complex scalar field has 2 real degrees of freedom. You can realize this in this way, but there is another way of realization of this 2 degrees of freedom of a complex field due to its real and imaginary part. You note that if phi is this, you can write phi is this 1 by root 2 is just a normalization factor I put. You can skip it or you can keep it, up to you. But if you take this, then you can see, you can write phi 1 and phi 2 in terms of phi in this way. Because it is the z plus z star is the real part, z minus z star by 2i is the imaginary part. Okay. So those, etc., etc. So, but this, if you, okay. So we can choose, so instead of choosing phi 1 and phi 2, we can choose phi and phi star as independent fields to express the dynamics represented by phi 1 and phi 2. So these are basically 2 bases, 2 sets of bases. In the whole dynamics of the system, you can either describe in terms of these elementary real fields phi 1 and phi 2, or in terms of phi and phi star, where you have to choose phi and phi star to be independent. Okay, this is just a rotation of bases, phi 1 and phi 2. If you turn it by 45 degrees, it will become phi 1 star and phi 2 star. Just a minute, just a minute. Okay, is it clear? So I want to describe the dynamics of the system. Now in our case, in this case, we have seen the dynamics, description of the dynamics of the system means investigating the equations of motion, or in other words, to construct the Lagrangian for the system at the first place. Now to construct the Lagrangian for the system, we need the basic fields in terms of which the basic coordinates, which are here the basic fields. Now for a complex Klein-Gordon field, I can choose the basic coordinates either as phi 1, phi 2, or as phi star. Is it clear?
Yes, sir.
Yes, sir, I have a question.
Yes.
You have said that pi 0 corresponds to the real scalar field phi, but my question is how field and particles are collected?
So that for that you need quantization of fields. These particles are basically quanta of these fields. I will. I have not reached that
Okay,
point.
okay, okay,
So
okay,
for
okay.
I just since you asked this beautiful question, there is a simple example. Suppose when you do a quantization, you get quanta in the sense. Suppose you have a harmonic oscillator, a single classical harmonic oscillator, okay, with angular frequency omega. Now its energy is p square by 2m plus half m omega square. Clear? Classical. Now, once you quantize this, you treat a quantum harmonic oscillator. What is its energy? Its energy is En equal to n plus half h cross omega. Clear? Now, the same harmonic oscillator, you quantize it. Earlier, it was a single harmonic oscillator. Now, once you quantize it, what you get? You get the total energy of the oscillator. Now, you can express in terms of as n plus half h cross omega. So, you can think that you keep that half h cross omega as the basis, as the ground level, but that n can be anything, 1, 2, 3, 4. Therefore, a simple harmonic oscillator you can view as if it's a collection of particles of energy h cross omega. There can be 2 particles, there can be 6 particles, like that. So that's how quantization gives you many particles from a single particle. So we will use this kind of this idea for quantization of the fields. So right now I can't associate these fields with these particles, but since you asked this question, that was the line of answer. But maybe after 2 or 3 or 4 classes after puja we can reach there. So there are many problems of this theory which I am discussing now, because it is relativity and quantum mechanics, and they don't actually their marriage is not good. They can't live together. Okay, we have to do something more. There one problem why they can't live together. That question you pointed out, Shaptosho, that because of this in relativity you have xt on equal footing. In quantum mechanics there is something. I mean, this position of a particle is represented by operator, and now also here you are treating x, not just space as parameter, but okay, so all these things are there. So these things will get automatically solved when you come to quantum field theory. But the aspects of this dynamics of this field we have to understand at this point, so that we can realize how it will look like in quantum field theory. Otherwise we can't, if we directly do quantum field, then we can't understand the physics of that. Before that we need this intermediate stage where there are, so to, I mean, to feel whether the I mean, how to feel whether a marriage is good. First you have to have a bad marriage and realize the problems, then you can feel justify, or then you can appreciate the positive things of a good marriage. So that's why now this marriage of relativity and quantum mechanics, just in this way, as relativistic quantum mechanics, has many problems, but it has many good features also. So we have to, so ultimately at the end of the day we have to take relativity and quantum mechanics together, but we have to do something to it. But that togetherness, taking them together, that has its own benefits, which is already there here. It has some drawbacks which we have to remove from this. So right now, so I am with that intention, I am discussing relativistic quantum mechanics here and physical interpretations of this. So how particles and fields are connected, that question can be answered, will be answered when we enter the quantum field theory. Okay, right now all these fields are classical fields. I mean, they are just mathematical functions. They are not operators. Okay.
Okay, sir, fine.
So you can take phi and phi star for complex scalar fields. Then their equations of motion will be same like this. If phi satisfies this equation and phi star satisfies this equation, but to break the complex scalar field in terms of its two internal degrees of freedom, here I mean two real degrees of freedom, that we have broken up in this way, not in terms of real fields, but in terms of complex fields, but considering phi and phi star. Okay, so we have to think that there are two equations of motion, one corresponding to the field phi and one corresponding to the field phi star. And we have, for this analysis, we have to treat phi and phi star as independent fields. Okay, like choosing phi 1 and phi 2, we call it dependent. So in other words, we can choose phi and phi star to be independent. So there are two equations of motion for complex scalar field. That means here in this general equation of Euler-Lagrange equation, this R runs from 1 to 2. Once for 1 R equal to 1, I have to put here phi. For R equal to 2, I have to put here phi star. Clear? Therefore, so let's do for a first again, let's do find the Lagrangian for a real scalar field where there is only 1 degrees of freedom, 1 real degrees of freedom. Field degrees of freedom, one field is needed in that degrees of freedom. Okay, so in terms of the Lagrange, so there is only one equations of motion, so this Lagrangian equations of motion should be this. Clear? Euler-Lagrange equation is this. So these two are equivalent. This is the general form of Euler-Lagrange equation for one single field phi. We have to find L and put it here so that we get this equation. Okay. Now we check this. If you do this, because you can, so Lagrangians are always find in this way. You look at this differential equation, form of this differential equation, how the derivatives appear, and you know the actual form of this equation, then choose a suitable L so that this is satisfied. Okay. Now since del L del phi is there, and this equation contains a phi here, that means L should contain at least a phi square, so that del L del phi gives you a phi and it comes here. So that's why this reason, and this coefficient should be m. Also, you can check to get this equation from this part should be like this, because if you take the derivative of this, so it is your work to verify during the puja vacation. If you take this form of the Lagrangian, put it here, you will get this back. And if you are intelligent enough, intuitive enough, just looking at this expression and the condition that L gives you this equation, you can write down L. Okay, these constants are arbitrary. Okay, you can leave it with this constant, but the form should be like this. Okay, and you can easily see also from here, you put, so this is the Lagrangian for Klein-Gordon field. Now, this is this Lagrangian contains all the features of this equations of motion. They are just different manifestations of the same information. One in the form of a differential equation, another in the form of a Lagrangian. Okay.
Sir, without the equation of motion, can we logically motivate the Lagrangian?
Without the equations of motion?
Yeah.
No. What? So, the logically for any.
When we are doing classical mechanics, we are motivating free particle by different symmetries, isotropy of space, homogeneity of space, like this. Can it be motivated like this in field theory?
No, because those fundamental aspects of space and time, isotropy of space and isotropy of time, you have already incorporated there. Okay, now, because here you have a field. Okay, here you have a field, even it is a free field. Okay, so you can't say about its, even space is isotropic or homogeneous, or time is isotropic or homogeneous, uh, uh, so L, in this case, L is not not a function of x dot or t dot. X and t are not the coordinates here. Here coordinates are the fields itself. In classical mechanics, when you say there are this q are the coordinates and q's, okay, q and t, then q had, when you applied homogeneity of space to find out the Lagrangian for a free particle, then you took q as the coordinate of the particle. That is the space. So you don't keep any in the free particle Lagrangian, you drop all q terms, only keep q dot terms, so that Lagrangian, free particle Lagrangian is same for all space. I mean, because this spatial homogeneity. Can you follow me? Because in the free
Yeah,
particle Lagrangian, q is there, and q itself is space whose homogeneity you are studying. Now, if phi field is there, you can't say phi is. There is no point of saying phi is homogeneous or not. Then your question comes.
yeah, right. Okay, okay. We can't say anything about phi because we.
Yeah. You can't say anything about phi at the beginning. We can
Yeah,
only
right.
say only the equations of motion. You can only arrive at this because this satisfies basic premises of quantum mechanics and relativity. That's the basic point. Without this, you can't proceed anything. You have nothing. How can you logically? I mean, where you will? Where logic will stand. Okay, so you have to have these equations of motion at the very first place to construct the Lagrangian. Even Lagrangian for a free field, because these phi's are not, you can't say anything about phi, whether they're homogeneous or isotropic. If you assume phi is homogeneous, phi is isotropic, okay, or there is no point, not phi is homogeneous, your system should be, then you have to assume that your system is, your phi is a homogeneous field. That means it has it has at a given instant of time, it has same value at all points. You have to assume that. Under that assumption, you can say your phi is independent of x. Then in this case, only x derivatives will not be there, if you assume that. So it is a special cases of assumption. Under assumption that phi is a homogeneous field, that means at every point in space, it has the same value. That is the meaning of phi being homogeneous. Clear? So it is independent of x. That is the meaning of phi being homogeneous in space. That we sometimes do in cases in cosmology also, to describe some kind of fields. We assume it is homogeneous. Then this Lagrangians, then we can say at least Lagrangians should not contain any functional dependence of grad phi. It will only contain phi dot. And then we can proceed. But you have to have an equation of motion to know the form of the Lagrangian. Yeah.
Yes. Okay.
So, but we are not in x and t domain, right? We are in the conjugate space. So having derivatives of x
Sorry?
and t won't be there.
Yes, it is not there. It is not there.
Yeah. So I mean,
No. What I am saying, x and t derivatives are not here. What I am here in this so what Lagrangian is a function of phi, say phi, and its in general space-time derivatives. Clear? Okay.
yes,
So
sir.
now what I am saying is that if you are doing a theory and you impose a condition yourself that your field phi xt, which is general function of xt, parameters xt, this is field is such that, this is your assumption, it is only a function of t. That means field is such that it does not depend on x. That means at all points in space, the field value is same at, so far as at a fixed time, at any time. Clear? So that is the interpretation of the phrase field is homogeneous in space. That is In classical mechanics, when we say space-time is homogeneous, that is a completely different thing. Here,
Sir,
if we say field is homogeneous, then you can say at least Lagrangian should be function of phi and phi dot only, not that space derivative will not be there. But what will be the form of the Lagrangian, that you can say from here. But in classical mechanics, since you are in that space, your coordinates are also related to this space, then you can exploit those space-time homogeneity and anisotropy to derive Lagrangian of a classical particle, free particle. But here, phi sits at the level of coordinates, not the space-time. They are okay. So you can just use space-time symmetries at the very beginning to find out Lagrangian out of nothing. We will use space-time symmetries later, but once we find out the Lagrangian, then we will come to that. May I proceed?
So, I mean, in
Yes.
principle, when we write this for equation number 46, shouldn't we write phi x and t since we are writing do nu do?
No. The x here
fraction of
x means this.
Oh, the 4 vector notation. Okay.
When I don't give a vector sign over x, it means space and time. Sorry. Okay. Always all x is here. All x means this 4. This x means 4. When I have to specify only the space part, I will write like this. This is the standard convention. This part means only x. Clear? So in my class note, whenever there is a phi x, so think this is x and time. All these x's are x and time, not only time, not only space. Okay. But try to, okay. So now is it clear that if this is the Lagrangian of this field, because if you put it here, you will get
when you're
this.
doing classical,
Hello? Okay, think of it. I think.
yes, when we are doing classical mechanics,
When you are doing classical mechanics, actually this Lagrangian looks like what? If you think phi as a coordinate, so if you remove this space part, I mean this is the 0, 0 part is half phi dot square minus half, there is like a like what? Harmonic oscillator Lagrangian. Clear? But only these, if phi's are these coordinates. If you want to compare it with a classical Lagrangian, this grad phi is there, but without that special dependence, it somewhat looks like classical mechanical Lagrangian, because this equation actually is derived from this equation. The energy momentum relation is same. Yeah. Okay. So right now, so what I request you, at every step, don't compare with classical mechanics, because then this class will not go forward. Okay. So let me complete what I am going to say. Then you compare what is the scenario. Once you get somewhat a complete picture, then you compare with your known classical mechanics and see what are the upgradations and what are the differences. Okay. So only thing is that here at this point, this L is stands for the Klein-Gordon Lagrangian for a real scalar field. May I proceed? Hello? Are you there?
Yes, sir. Yes, sir. Proceed.
Okay.
Yes.
Okay. Now, when there is an equation, when you have a complex scalar field, when the Lagrangian, then I said that actually to study the different independent aspects of the field, you have to consider these two equations, which is equivalent to considering these two equations in terms of phi, in terms of these real parts, or replacing these two degrees, these two free degrees of freedom are also inherent if you consider inherent but explicit if you consider these equations of motion in terms of phi and phi star. Okay. Now you have to consider these two phi and phi star independently. Now one is this equation, Euler-Lagrange equation, another is the Euler-Lagrange equation. Clear? So you have to find out L such that if you put L in these two equations, you will get these two equations, the same L. The equations in equation 52 and 53 are same L. If you put this L, put the Lagrangians here, you will get these two equations. And that will give you the Lagrangians for complex scalar field. And you can check if you take this Lagrangian, it's a very crucial check. You use this Lagrangian in the first equation. Actually, you have to intuitively looking at these equations of motion and form of the general form of this equation, you have to construct this form by trial and error. If you are wise enough and intelligent enough, then you can make it at the very first try. Now, this is the backward way of calculating or constructing Lagrangian. Lagrangians are always constructed in that way. Okay, from a given Lagrangian, there is no other ways. From a given equations of motion, you have to reach here using this. So what you have to take? So that you have to take. Okay. So if you put it here, you see this equation is all derivatives of with respect to phi. No phi and derivatives of phi. No phi star in the first equation. Therefore, look at this equation carefully. And these are very, very important and crucial things for rest of your MSc courses and if you study physics in future. This part is this part contains the star. First thing is a star. So Lagrangian is a real number. So this should be like this. Now if you put this Lagrangian here, you will see phi will, so what will be this term, del L del phi, can you tell me?
M square phi star.
M square phi star. And this term, del mu phi will, this del mu phi will be cancelled, but so this will remain. Clear? But there is an extra del mu here. So there's del mu, del mu. So if you put it here, you will get the second equation. Am I right? If you put this equation here,
Yeah. Yes.
and if you put the second equation, sorry, this Lagrangian in the second equation, you will get the first equation. Is it clear? So the same Lagrangian, yes.
Minus m square phi star will come, but there is plus m square phi star. How is it matching? I can't get it. I think it is naive, but still.
No. This, see, here is a minus sign.
Yes.
There are two minus signs here and here. So if you put it here, if you put L in the first equation, del L del phi will be minus m square phi star. And this term, if you put L here, will contribution from this. So it will also come with a minus sign. These two minuses will make it plus.
Okay.
You check it. This is trivial. Okay. So I say this is the Lagrangian for a complex scalar field. Now, if you wish, you can write it by writing phi as phi 1 plus I phi 2, phi star as phi 1 minus I phi 2, can write it in terms of phi 1 and phi 2. Okay. But this is the, so this is the summary for a real scalar field. This Lagrangian is like this. And if you break it up by open this contraction up, you will get phi dot square minus half grad phi square like this. For a complex scalar field, these things happens. Okay, so you will get this kind of thing. Remember, Lagrangian should be always have some properties. Lagrangian is, so this half constant is arbitrary. You can multiply here also by some constant, but same constant for both terms. Okay. The thing is that Lagrangian has to be a real number, first, a real function. Secondly, Lagrangian has to be a Lagrange scalar. It should be a scalar quantity. Lagrangian is always a scalar quantity. It is not a vector. So under Lorentz transformation, Lagrangian density should remain invariant. Then you can see this forms supports that. Since phi is a Lorentz scalar or does not transform under Lorentz transformation, and del mu phi are just a covariant and contravariant vectors. They are also Lorentz scalars. So also this term. So Lagrangian is a Lorentz scalar. Under Lorentz transformation, you can easily check that this Lagrangian will not change. Okay. So whenever from now on, whenever we will deal with Klein-Gordon field, I will forget about everything and just starting point will be this form of this Lagrangian. Then we will study, investigate what is said, what is inbuilt in this form of this Lagrangian. And from that Lagrangian, we will try to extract all the physics. So this is the extract. Okay. So honey extracted from a flower, you put it in your room. You take that honey. Okay. So you take the whole effort of the tree in producing the flower, everything is there in that honey. So this Lagrangian is that. Okay, so this is the starting point, and this will also be the starting point of quantum field theory. Whenever we study quantum field theory, so we will study the same Lagrangian. The Lagrangian is same. Only thing is that this phi's will be operators. Okay, in that case Lagrangian is also an operator, so also Hamiltonian like that. Okay, we don't discuss about this right now. This is the summary of this. Is this clear?
Sir, do we still
Yes.
consider Lagrangian as kinetic minus potential energy?
You can call this as kinetic term, potential term, but now this word energy you have to redefine. You have to redefine what you mean by energy of field. It looks like kinetic term, okay, because kinetic means there is some motion associated with it because time derivatives are involved. Okay, but you have to really, when you want to really find out the energy for a system which is represented by field, then you have to find out what is the energy carried by the field. That is the energy. Okay, and we will see that energy, form of that energy, that is not energy due to motion of something, motion of a particle. That is the energy of that field. And field has its own space-time dynamics at every point in space time. Clear? So you can call this loosely as kinetic term and potential term by matching it with thing, but you have to give, if anyone asks you what do you mean by kinetic, you have to properly, you can't say it is the kinetic energy of that field, because what is kinetic energy of that field? You have to feel. That is a, I mean, that word you have to also define. It is not like, so we will define this, we will see that later. But right now no need to call this kinetic and potential. Okay, so I am not introducing those terms at this point. Okay. So
Sir, these derivative terms in real scalar field or complex scalar field, should it be always bilinear in fields? I mean,
yes,
the derivative occurs twice.
So far as it is a free field. Free field in the sense that so far as this is the energy momentum relation from which by replacing E and P by operators you got Klein-Gordon equation, and this is the energy momentum relation of a free particle. Clear? Momentum is a momentum. If it has some extra potential extra kind of energy which is not free, say V of x, sorry, then the equation of motion will get different. Then this field will not be quadratic. I mean, field power will not be 2 here. We will see that. But so far as free fields are concerned, it must always be quadratic.
Okay, sir.
Because you can, okay. There is how, and this is a very, this is a, I mean, huge physical significance of this, why it should be quadratic. Now, if there are interactions present with this field, we are discussing about free fields. Free field equation means, look at the Klein-Gordon equation. These are equations for free fields. Sorry. These are equations. Oops. These are equations for free Klein-Gordon field, free Dirac field. Now, when there are interactions, they are not zero. There will be source term. There should be some function here. Okay. Then this Lagrangian will no longer be bilinear of the fields. Okay. But I will explain this when it will come. It is not an easy thing to understand, realize. I mean, at all these cases, we need quantum field theory. But at this point, you can see, since energy, I mean, for free fields, the energy momentum relations are quadratic. Okay, E square equal to P square by 2m. That same thing comes here in the Lagrangian. That is a reflection of that somehow. Because that is the form of, because that is a reflection of this, that reflection is there in the form of the equation. So also in this form of the Lagrangian. Okay. So, okay, how much is done? Now we will study the Lagrangian for a Dirac field, and that is the most crucial and technically clumsy concept because of this reason. Okay, so let me take a break for 1 minute.
Hello, sir.
Yes, sir.
In page number 114, last line complex scalar field and Lagrangian equal to del mu phi star del mu phi minus m square phi star phi equal to phi star dot phi dot. This will get by writing the mu and mu explicitly.
Yes, yes, yes. So this is a sum. So if you first put
Yes,
0,
sum
0,
number.
so first term 0, 0 will give you time derivatives of these two fields, which is this term. The next terms will give you 1, 1, 2, 2, 3, 3 space derivatives. So which you can write like this.
Okay, okay, okay.
See, so if you would, I request all of you to do all these calculations explicitly and convince yourself. Don't just stare at the class notes when you are studying it. You have to do it explicitly, otherwise you will miss everything. Okay. Now, even Klein-Gordon equations are very straightforward. Dirac equations is more complicated, but let me take a break for a minute.
Sir, one question.
Let me take a break for a minute. Okay, then you can ask this question. Okay.
Okay.
Ah, so you can ask this question. Who are asking?
Sir, can we find? Sorry, can we arrive at Schrodinger equation from the second equation?
Yeah, that is your home task. Which equation? Sorry, which equation? Schrodinger equation from?
This complex scalar field.
No, 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 no. See, Schrodinger equation is a different equations of motion. Here, now okay. So here, in this Euler-Lagrange equation, if you put L as this, you will get equations of motion for complex scalar field. Now, Schrodinger equation is not a relativistic equation. It is a different equations of motion. Okay.
So, like in any relativistic, classical normal relativity, we can take the non-relativistic limit, and it will give like exactly like non-relativistic case. So, is that happen in this case? I mean, in this
But
case.
sir, here Schrodinger's equation is linearized, but Klein-Gordon equation is not linearized. It's a squared psi equals to del
One
t
thing is
square.
that, so let me, I will not do this in my class. You try to find out a Lagrangian which, when put in the Euler-Lagrange equation, will give you Schrodinger equation. Do you follow my point? Can you find out a Lagrangian which, when put in Euler-Lagrange equation, gives you Schrodinger equation? And that Lagrangian will obviously not have space-time on equal footing, like in relativity. You can see books there.
So this is done in classical mechanics by Stein's books. This is an exercise.
Yeah. It's an exercise. Okay. So there you can put, but the thing is that, so what is your question? Your question was whether I can arrive at Schrodinger equation from these equations.
In taking the limit, I mean, taking non-relativistic limit.
Taking a non-relativistic limit.
In classical mechanics, we do sometimes.
No. In classic, you take non-relativistic limit of what?
Like some in like Lorentz transformation. If you take v very small, then you can actually go to Gaussian transformation.
Now here you can't do, because quantum mechanics and special relativity, so it is, this theory is not just an I mean, it is not just a so what should I say,
Extension of
extension, and not just that trivial extension of classical mechanics, because here this because philosophically, quantum mechanics and relativity are, there are structurally not matching with each other. Okay. Now, so tell me first, how you will take, what do you mean by taking the non-relativistic limit? That is a simple word to you. So when you go from Lorentz transformation to Galilean transformation, what you are saying, from relativity, special relativity to classical mechanics, when you take that non-relativistic limit, what you do, you take V by C tends to 0.
0. Yeah.
Now, so now in this
It
context,
does not actually it does not actually structurally go to non-relativistic, relativistic to non-relativistic. Just we are ignoring the VYC part. That
yeah. When your V by C, V is very less than C, then the equations will effectively become Newtonian equations.
Yeah.
There. Now here, the thing is that, so what do you mean by taking the non-relativistic limit? Whose speed you will reduce? So
Sir, in that case, the
here
something like
actually the effect, the way relativity are being incorporated, we are trying to incorporate in quantum mechanics is by using the equal time, I mean this E square equal to P square relation, which is a, I mean, same, either in Dirac equation, either it is linearized form, or in E and P are of same order of, I mean, same, E and P are in same degree. That is the jump from non-relativistic quantum mechanics to relativistic quantum mechanics, and that is not a continuous thing. Do you follow? In quantum mechanics, you use this relation, non-relativistic quantum mechanics. You use this relation to get Schrodinger equation, quantize this energy momentum relation. You use the prescription of replacing E and P by operators in this relation, but in relativity in these relations. Okay.
Yes, yes.
Now there is no limiting case here. There is a discrete jump from this to this. So you can, this concept of going to relativistic limit does not exist here in case of fields. If a particle is moving very fast and slow, then with velocity being a continuous parameter, you can change it. But here, where we are implementing the effect of relativity, just by doing this jump. Now you can't take P2, sorry, you can't take E2 to U1 continuously. There is the meaning to that. There is a power 1. Okay, so that relativistic, taking a relativistic limit loses its significance, physical significance here, because you can't do that in this context.
Structurally, one cannot
Yeah,
go.
structure is different, completely different.
Sir, I have one another question. It may not be related to exactly this point. Like you have previously in previous classes said that in general, when there is some relativistic case, then we call that yes field equation. Uh, Roughly, you have said this, but
Actually,
not
actually,
necessarily that. Like I mean, in fluid dynamics
no,
equation or
actually, in conventionally, field can be anything, but this electromagnetic field and gravitational field. So you have a course classical field theory 1 and 2. You
yes,
remember in your that
yeah,
the word classical theory of fields, that is reserved for electromagnetism and general relativity
yes,
and gravitational field. Okay, but that does not mean there cannot be any kind. There can be fluid velocity field is there. Any kind of field is there.
they are in those like let's say fluid dynamics.
So anything which
Uh,
depends on space and time, you can think of a field.
I mean, sorry, just want to ask in fluid dynamics, there is a T that equation do depend on T and X, right? I don't know exact equation, but they do depend on X and T. So
Yes, yes.
those X and
Those are
T,
also fields. Those are also
yeah,
fields.
yeah,
Yes.
those X and T are this X and T. I mean, are structurally different, right?
Structurally different
No,
means,
I mean here in relativity, in normal relativity, structurally we are taking T as
no,
a
space and time are space and time. When you say structural difference in space time, as you were saying, these x and t and those x and t, that means, but so far as the metric of space time is same, there it is also Minkowskian, here it is also Minkowskian. Unless we go to a curved space, it will be structurally space time structure is same. But what is structurally different is the, what should I say? The
time depends on relativistic case. Time depends on velocity,
no, no,
but
no.
they are
Say the dispersion relation there.
yeah.
Here, actually, you can So if you have this kind of question, try to verbalize it in a proper way and write in mail. Okay, so if you have more thoughtful questions, first write it to mail so that I can realize it what you are asking, and then we can discuss over mail, and then we can, if things are not clear, we can discuss over this Zoom meeting. Okay.
Sure, sure, sure.
Okay. Now, okay, I have half an hour. Okay. So Dirac equation. So for this, so this is the form of the Dirac equation. You all know this is the Dirac equation. This is, but psi x is a 4x1 column matrix. And in general, psi will have complex elements. Yeah. So special cases, it may be real or not, but it is complex. So this part is a 4x4 matrix. Clear? All of you now know this. This is a 4x4 matrix. This is 4x1 matrix. Now the thing is, we want to find out a Lagrangian, which when put in our Lagrange equation will give you this equation. Okay. Now the thing is that, let me first find out how many. So this is a 4x1 matrix. Okay. Now the thing is that in general, or leave it. So this is this object is in general a complex object. Like if it is a real object, then it is a single object. But if it is a complex object, even if it's a single object, it has 4 components. But it is a complex object, then just like in Klein-Gordon equation, what we did, we ultimately break it in 2 equations of motion, one satisfied by the real part of it, another satisfied by the complex part of it, so that the actually 2 real degrees of freedom a complex Klein-Gordon field has ultimately gets showed up in this Lagrangian or in the form of these 2 equations. Okay. Similarly, Dirac equation, the first point is that this phi can be complex. Therefore, it has, so far as it has at least 2 degrees of freedom, in the sense that the real part of it and the complex part of it, that has to, we want to treat them independently, so that we want to feel the, what is the physical significance of these 2 parts. Okay, so while discussing the fields, the system, instead of choosing the whole Dirac field or like complex scalar field as a single field, we have seen this in terms of, we try to realize it in terms of 2 real fields. Here also, the Dirac field psi, we try to realize in terms of its, in terms of it and its complex conjugate. Clear? So now the thing is that, what is the complex conjugate of phi? Unlike Schrodinger equation, unlike Klein-Gordon equation has that simplicity that the phi satisfies the equation. If you star it, there is no I here. So phi star will satisfy the same equation. Yeah, so phi and phi star satisfy the same equation. Now the point is, what will psi and psi star, what is psi star? Will psi star satisfy the same equation? That is the first issue. So first we have to define, observe, what is the just the complex conjugate, whatever it may be, complex conjugate, which equation it is satisfied by this. It is obviously not the same equation because it contains I. Okay, if you make the complex conjugate of all things. Okay. So just I have written something here. Let me read it out. I don't forget what I have written. To find Dirac Lagrangian, first make the independent degrees of freedom of the Dirac equation explicit. Okay. Just I want to make this reality and complex, this real part and imaginary part explicit in this Dirac equation, so that we can probe what is meant by them. We want to go into the meaning of this real part and complex part of the Dirac wave function itself or Dirac field itself. Now, for that purpose, we have to look for the equation of motion satisfied by the complex conjugate of psi also. Okay, what I said. Now, note that the Lagrangian, whatever it may be, should be a Lorentz invariant function, which is a single component object. Now, the Lagrangian, which you ultimately want to construct, which now I expect it should be a function of phi, Dirac field, del mu phi. And if I want to make this the two real parts of phi explicit, I can express that in terms of phi and phi star also. So there are two fields actually. Is this clear? Is this setup clear? Really, if we want to make this real part and complex part in psi explicit in the Lagrangian, to make that explicit, that can also be done by considering psi and psi star separately. So basically that is doing psi plus psi star by 2 gives you the real part of psi. Okay, but so you choose the basis as psi and psi star instead of real part of psi and imaginary part of psi. Okay. Now if you do that.
Hello.
Yes.
So Lagrangian have to be a single component always.
Lagrangian, because there is a function, single component. It can't be a matrix. Can't be a matrix means we deserve that it can't be a matrix, because Lagrangian is a function whose d4x integral should give you the action. If Lagrangian is a matrix, if d4x give you a matrix, and we can't apply action principle. d4x is minimized. So what do you mean by a matrix is minimized? For that, for remain action as a function or a number, we need Lagrangian to be a number only, a single number only. That means a 1 cross 1 matrix. It can't be a matrix. Otherwise, the whole point of doing the action principle, formulating the action principle will not work. Clear?
Yes, right.
Therefore, that's the requirement of our formulation, that Lagrangian should be a single component object, but it contains phi star, okay. But to construct a single component, it is a single component object, but these are all 4 cross 4 matrices, 4 cross 1 matrices, psi star, okay, 4 column matrices. Now to construct a single component out of this 4 psi and psi star, all these are 4 cross 1 matrices. We must, in this functional form, we must somewhere multiply or make use of transpose of psi to make it a single component object. Clear? To multiply somewhere, use the fact that 1 cross 4, you have to 1 cross 4. You have to multiply these things by some row matrix ultimately to get it a single component object, because all these are all 4 cross 1 matrices. So it can't just be a function of that. So the other elements involved in this Lagrangian must be of the form of, at least we are constructing it, so we require some 1 cross 4 objects also in order to balance that 4 cross 1 structure to finally lead to a 1 cross 1 Lagrangian. Am I clear?
Yes, sir.
To construct the single component object L out of psi, it will be useful to take the help of transpose of psi together with psi. Okay. Now transpose, now there is one important thing, that so it should contain transpose of psi, but it should also contain psi star to make the 2 degrees real degrees of freedom explicit here. Therefore, but since psi dagger is a matrix which is this, which is complex conjugate of psi then transpose. That means psi and psi, this psi dagger, instead of this transpose, if we use psi and psi dagger, it will automatically contain the complex conjugate of this psi. So if I just write it by replacing this dagger by psi dagger, so I have to construct Lagrangian in this form, then I have already taken care of the complex conjugates of psi inside psi dagger and also the 1 cross 4 and 4 cross 1 thing, so that while constructing Lagrangian, I have only to specify that psi and psi dagger should be multiplied. Psi dagger first, then psi dagger, so that then psi. Is it clear? Psi dagger psi is always a 1 cross 1 element. 1 cross 4 into 4 cross 1. So it is, we are using that logic to write Lagrangian in this form, in this functional form. So basic elements to write this Lagrangian will be this. Clear? Instead of psi star, because is this clear? This is very crucial. Is this clear? So basically we have to find out what is the Lagrange. This is the equation of motion satisfied by psi. What equation of motion does psi dagger satisfies? Okay. Psi dagger is a 1 cross 4 row matrix. Psi is a 4 cross 1 column matrix. Here. Now let us find out what equation. So basically we will have 2 equations of motion, one for psi, another for psi dagger. The equations of motion for psi dagger will contain in it the complexity of psi, the complex conjugate of psi. Therefore, the real part and complex part of psi are automatically taken care of in these 2 equations. One is the equation, the normal Dirac equation, other is the corresponding equation for psi dagger. So from Dirac equation, we have to first then find out what is the equation satisfied by psi dagger. If psi satisfies this equation, what is the equation satisfied by psi dagger? Okay, for that, clear? So this is the motivation for looking at this. So I am taking dagger of this and clear. So, but to find that the equation satisfied by psi dagger, I am taking complex conjugate and transpose, that is dagger of this. Okay. Now can you tell me what is this? Dagger of this, A dagger, B dagger. So first matrix, so be very crucial about this. This is how much? This is a square matrix because gamma is there. This is a 4 cross 4. Again, this is a 1 cross 4. Sorry, this is a 4 cross 1. And the product whole dagger is 0 because right side is 0. So taking transpose complex conjugate both sides, you get this. Now A dagger, B dagger is equal to, okay, I just multiplied it and then write it. So this is the thing. Now, what is this? This is A minus B whole dagger. Okay. Is this. So this dagger minus this dagger, but this whole dagger of this will give you minus sign for I, and here there are 2 matrices. One is gamma, one is delta mu. Then I am taking this dagger, so A dagger, B dagger equal to B dagger, A dagger. Okay, so here we use this relation. A dagger, B dagger equal to B dagger, A dagger. So this is used in this second in obtaining this to this. Is it clear? Tell me if you have any doubt in understanding this equation 55 from here. Is it correct? Can't see.
Yes, sir.
Clear. Now you are be very careful because you are handling matrices. and that too, some are column matrix, some are row matrix, some are square matrices. So be very careful about while taking daggers or while taking matrix multiplications, etc. So our first point is to find out what is the equation satisfied by Psi dagger. Okay. Now I see, you can see that this is the equation satisfied by Psi dagger. Clear? This is the differential equation satisfied by Psi dagger. Okay. Now let me do something. So you know this is the form of this Dirac Hamiltonian. Okay, this is the Dirac Hamiltonian here. So when we, or the energy, if you say, linearized energy momentum relation, we square it and get it this Dirac equation by introducing the wave function here. Now, since Hamiltonian, if you look at in terms of this Hamiltonian operator, quantum mechanical Hamiltonian operator, relativistic quantum mechanical operator, then Hamiltonian is a Hermitian operator. Okay, so also momentum. Therefore, Hermicity of Hamiltonian will give you this. This matrix should be, so sorry, Pi is okay. So do you know? Okay. So this is, can you follow? This gamma 0, gamma I should be a Hermitian matrix. And gamma 0 should be a Hermitian matrix, so that the this Hamiltonian, when I will write it in terms of an operator, has to be Hermitian. Because of that, this coefficient matrices should be Hermitian. Clear? That means this should be true and this should be true. Have you done this in quantum field theory course?
Yes, sir.
Oh, then you know. Okay, sorry. Then you know what is gamma mu. So what is gamma mu dagger?
Gamma 0, gamma mu, gamma mu.
Okay. Okay, you have done that. Okay. So okay. So that's written here. So this is gamma mu. Okay. Sorry, you did that. So, or if you have not done that, you can look at this letter and see. This is an identity, true for all gamma matrices. Now, therefore, here in place of gamma mu dagger, I can put this. If you put it here, you get, so if you put, so in place of gamma mu dagger, I again wrote this, you will get this equation. Okay. And now look very carefully. What you do, you multiply both sides by gamma 0 from right, this side. Multiply by gamma 0. Multiplying by gamma 0 makes us to exploit this identity. Gamma 0 square is 1. Therefore, this will be Psi gamma bar gamma 0. And here there will be gamma 0 square in this term. And gamma 0 square is 1. So you get the first term this without this gamma 0 here. Or since what is gamma 0 dagger? Gamma 0 dagger is equal to product of 3 gamma zeros. Product of 2 gamma zeros is 1. Therefore, gamma 0 dagger is gamma 0. Therefore, here I can sorry, what have I done? Okay. Okay, sorry. We don't need gamma 0 dagger. I just clump gamma 0 with Psi star and put the bracket here so that to make it look like same. Okay. Now this is, so the same, this is the equation satisfied by complex conjugate or the adjoint of Psi dagger. Okay. Now, instead of, to make this equation to look simpler, we just put our Psi dagger gamma 0. Okay, so this as this. because shy dagger, what is shy dagger? Shy dagger is a 1 cross 4 column matrix. Okay, if you multiply by another matrix, constant matrix gamma 0, which is a 4 cross 1, 4 cross 4 matrix, okay, then the entire matrix remains 1 cross 4. And we define that matrix as psi bar so that we can write it simply like this. So that instead of psi bar, we just multiply by this constant and constant cap and this. So psi bar and physically psi bar and psi dagger contains the same set of informations because they only differ by this constant matrix gamma 0. Therefore, in terms of this psi bar, we can write it in a more precise way in this way. And we can say that there are, instead of psi and psi dagger, as we were started saying this, instead of psi and psi dagger, psi and psi bar, where psi bar is related to psi dagger by this, psi and psi bar can be taken as these two basic aspects of the Dirac field, two basic aspects in terms of which the dynamics of the Dirac field has to be investigated, because these two fields together captures the the 2 degrees of the real and complex degrees of freedom of the Dirac field. Am I clear? So we can say now, one is the Dirac equation, other is this equation. In other words, so we write these equations of motion satisfied by a Dirac field and its adjoint together expresses the internal degrees of freedom of the system. Here degrees of freedom means the two real and complex, those two internal degrees of freedom, not other degrees of freedom. So these are the two equations of motion. First one is the normal Dirac equation. Second one is the equation satisfied by psi bar, which is basically psi dagger into gamma 0, which therefore contains the complex conjugate of psi inside it. So these are the two equations of motion. Okay. Now we have to construct a Lagrangian such that Lagrangian involving what? We have to construct a Lagrangian involving the Dirac field, their space-time derivatives, the conjugate or the adjoint Dirac field and their space-time derivatives, so that when put in Euler-Lagrange equation, this Lagrangian will give you these equations. So that Lagrangian will be Dirac-Lagrangian, and obviously, since Dirac-Lagrangian has to be a single component object, that psi bar and psi being row and column, they must appear whenever they come, they must appear together. So that Lagrangian should also be quadratic in nature or of degree 2. One psi and one psi bar must be there in every term of the Lagrangian. Otherwise, it will not remain a single component. Clear? Is it clear?
Hello, sir. Can I ask a question which is out of context? Means in our quantum field theory course, we are using the convention eta mu nu equal to 1 minus 1 minus 1 minus 1. Time component is positive and space components are negative. In your class, what convention are you using? Can you please tell me? Then it will be easier
Because I
for
have
me
not
to do
used
the
any
calculation.
convention. I have not used any convention yet because I have telling all the things generally. Conventions are needed once you need an explicit form of eta mu nu. Unless you don't need it, why you will use it? So,
Sir, you have used the convention earlier
Yes,
where?
when you
in
write del mu 5. You have used
del mu
plus minus
5.
minus.
Yes.
Where? Sorry. Where?
Scroll up.
Here.
Yes, here.
Okay.
Plus
So,
minus 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 you
Plus
have
minus
used.
minus तीनटा minuses.
But plus half m square, how it is minus half m square phi square?
that is a mistake.
Oh, so second line also mistake.
Yeah. Okay. Those mistakes you correct.
But convention, I think you are following +1 -1 -1 -1. It seems so.
Yeah. So if you want to write it this way, is it? I don't think so. Just a minute. Or you can say 1 -1. Yeah, you are saying this.
Yes, yes.
Okay. Okay. So it may be this. Okay. So don't bother about this point of time, because I just write it to show you the space-time derivative, how it looks like, but we will always fix to this point. So far as you are related, I mean, we will always stick to the general forms. We will not go into the explicit form. When we want to know the explicit form, when we want to solve the Dirac equations or anything, then we need the, convention of the metric. Okay.
Okay.
So for my course, convention is, you can take any convention. Because if you take the other convention, what will happen? No, I am a bit confused.
Some things might differ.
No. Just a minute. So my convention. Just a minute. Okay. I'm a bit confused about something. I'm not telling here right now. But so if you find out what is the convention there. But these are just don't bother about conventions for this class, unless we don't need any explicit form of vitamin U right now. So all these things are independent of, all these forms are independent of any particular convention of vitamin U. Metric. Clear? So
Okay,
basically
sir.
So basically, are you following? So I think I should stop here, because we should go very slowly to realize these things. Otherwise, if I jump into my next point, it will be difficult. So tomorrow I will finish this. Only thing is that, remember, I have to construct a Lagrangian out of psi and psi bar. And this Lagrangian should be single component, it should be a Lorentz scalar, and the most importantly, when put in the Euler-Lagrange equations, now there are two Euler-Lagrange equations. Okay, one for psi and one for psi bar. Here, when we put that Lagrangian in those two Euler-Lagrange equation, somehow we should get back these two equations of motion. That in that way, in that sense, we have to construct the form of this Lagrangian, or we have to guess the form of the Lagrangian. Okay, so I will do it in tomorrow's class. Okay, so the point is, tomorrow when is the class?
11 a.m.
Is it possible to make it 10:30, or will remain asleep?
Okay, sir. 10:30 is okay.
No, I am asking everybody.
Yes,
Is
sir, it will
10
work.
is 10:30 be too early morning? Okay, so tomorrow at 10:30. Okay, because tomorrow I have to finish some things, and it can be open for discussions. There will be no class after tomorrow before in October. Okay, thank you.